Is optimal power flow? Well, we will see this in 2 weeks, in 2 weeks and a half, in fact. As we will see, this is one of the central optimization problems in the operation of power grids, of electrical power grids. In its generic form, we can cast it as follows: minimize the cost of operation of a grid, subject to constraints on grid operation. Grid operation are voltage, line currents, sometimes expressed also in the form of apparent power constraints, and on control variables, which are the set point of generators. How much should a diesel generator run, for example, but also the set points of capacitor banks, batteries, tap changers. Capacitor banks and tap changers are devices that are here to control the voltage in a grid. Batteries are devices that start to be deployed, that have been deployed very recently in order to solve problems due to overload, or to also help the grid when there is not enough local production. Load management actions, what is called demand response, that will be the topic of the following module. This is when we stop serving some loads because there's not enough capacity, for example. The cost is the cost of generation in its primary form. That's the monetary cost. If you run a fuel-based generator, that costs money, which is the fuel, whereas if you can live on renewables that have practically zero operating costs, of course, that makes a difference here. Sometimes also we introduce in the cost, we'll see that several times, what is called soft constraints, which is a way of making penalty for violation of voltage, for example, easier to manage. We'll talk more about that when we talk about MPC in a few more hours. Let's see an example. Here is a toy example of a grid that has 3 generators, G1, G2, G3, and at the same buses where the generators are located, there are also loads, so consumers. And here in this toy example, I'm using round numbers. I'm assuming the consumers want to consume 100 megawatts on each of the top nodes and 500 megawatts at the bottom node. And I'm assuming here also that the consumers are not flexible, which is mostly true today, but in the future, in modern grids, will become less and less true. Here, I'm assuming those demands are inflexible, so they must be satisfied. And for that, we have 3 generators that have maximum power production shown here, 400 megawatts. So the total capacity is sufficient. We have 700 megawatts of demand, 1,200 megawatts of potential production. But of course, there are limitations on the lines. Here, the grid is a full mesh, which is not very typical in distribution network, but is very typical in transport network, transmission network, the higher voltage network. Here I have 3 lines, and each of the lines have limits that are typically, line limits are expressed in forms of current limits, but here also very often, to simplify, they're expressed in the form of apparent power. So here 300 megawatt or megavolt ampere, because it's apparent power for all lines except line 3, which has a smaller capacity. So as we see here, the capacity of the grid is limiting. We have much less capacity on any of the line than the total demand or the total potential production of the grid. Therefore, we need to control where the power will be flowing. This is done with an optimal power flow. An optimal power flow problem, in this case, the only thing I want to minimize is the total cost of the generators. I'm assuming here very different costs. So generator 1 has a cost of, for example, here, a very medium value. Generator 2 has a very small value, and generator 3 a large value. Why would that happen? Well, generators have different costs for various reasons, depending on the technology. Some generators are consuming fuel. We can also add a CO2 penalty for the fuel when this fuel is not renewable. So that may make a different cost. There's also different technologies, different points in the life cycle of a generator that may make the operation cost, monetary cost very different. So that's what happens with those three generators. How do I express this? My goal is to compute the set point of the three generators. Of course, I could generate locally. Mostly, I could generate, generator 3 could generate everything except 100 megawatt, and the remaining 100 megawatt could come from the rest of the grid. But here, the cost of generator 3 is, in this case, very expensive. So I would like to really use the grid. Technically, how do we do this? Well, we formulate an optimization problem where we minimize the sum of the costs. Some values, control values, are the generator set points here that are assumed to be flexible, subject to constraints. So constraints are the grid operational constraints. Typically, the voltage magnitude at the three buses here should be within 5%. That's a very frequent value we find of operation of the nominal value. Why do we have that? Well, if the voltage becomes much higher or much lower, many devices will not operate properly. So they will simply disconnect from the grid. So that's a safety constraint that is present on most devices here. Line current intensities also typically are important, because if the line current is too high, the lines will heat up and insulators might get damaged. Also, there are losses. The branch flows are here expressed on the form of 300 megawatt mega VA maximum capacity. If we have intensity and voltage constraints, we typically don't need branch flow, but we will see that sometimes it's more convenient. And there are, of course, constraints on generation limits. For example, here, the generators can produce only, they cannot consume, so they can produce between 0 to 400 megawatts. They can also produce reactive power, so between minus 80 to plus 80 mega volt ampere reactive here. So those are the constraints dictated here probably by the technology of the three generators. How do we solve this? Well, we can use all the techniques we have seen in the previous weeks to when we know how to express the electrical state of a grid. The electrical state of the grid is given by what I call here V sub I, which are the complex voltages at the three buses here. And I know how to express the injected power at a node as a function of the complex voltages and the injected current. So the injected current is given by this. The product in complex terms of the complex voltage and the conjugate of the injected current is the injected complex power, which is the apparent power. The real part of it is the active power, the part that we're really interested in, and the complex part is the reactive power. So this is the first constraint here. So this constraint is expressing how the physics of the grid, how the injected power is depending on the complex voltage, which is the physical state of the electrical grid. Now we can relate the complex power here to the economical quantities of interest. So the injected power GI is the reactive power that this generator is sending here. And the QI is the reactive power that this generator is injected. The load, and here I'm expressing that at bus 1, the injected power is the algebraic sum of the injected power of generation, which is counted positively, and the injected power of the load, which is counted negatively. Here we have therefore minus Li, that's the active part of the power here. And here, to simplify, I'm assuming that the loads have a constant cos phi, a constant apparent factor angle, apparent power angle, which is more or less true. It depends, of course, on the devices, but this is to simplify the point. In reality, we would need also to be able to predict at least a margin, not a fixed value. So this equation at node 1 and at node 2, and node 3 as well, by the way, is expressing the fact that the total power here can be decomposed into the two sources of power that are shown here. Here, another constraint is the fact that the complex power is 1. So here it's complex power 1. That means the module is 1 and the angle is 0 at one bus. This is expressing a common practice that we find in practically all grids, that one bus serves as a voltage reference here. It's called a slack bus here. If this grid is interconnected to a higher level grid, if this is, for example, a mid-voltage grid connected to a high voltage grid, this would be the point of connection to the main grid. If it's a standalone grid, like on this example, then the typical operation is that one of the generator serves as a reference for the voltage here. This is how the other generators will work. They will capture the frequency from and the angle of from this one here. So that means that we set this complex quantity to 1. The voltages at the other buses are not defined, they are control variables, but we impose that their magnitude is within the bounds here. Here we're also imposing the power flow. Here you recognize VI times Yij, VI minus Yj. The second term is the complex intensity from node I to node J, multiplied by conjugate multiplied by VI, that gives the power flow from I to J. If I take the module of this, I have the apparent power, and here I have a constraint on apparent power. I can also have a constraint on current. Here I'm showing both. Very often we have only one of the two, because the first one often serves as a proxy for the second one. Here I'm also adding the generator capabilities that must be added as constraints here. So this is the formulation. Now, the variables I have are the complex variables V, I, S, and the real numbers G and Q. All G and Q are my control variables, the things I really want to control. S is an intermediate variable that comes very easily from here. And V and I are the hidden variables that result from the physics of the system. So I have now an optimization problem. If the size of the problem is very large, we have a very nasty optimization problem, and we will see techniques to simplify it. If it's small, like here, I can ask a brute force optimizer to find an optimum point. As we will see, there may be multiple operating optimum points, but the optimizer will find one that is close perhaps to the default operational values of my grid. This is what I did in MATLAB for the values that are shown here, the values of the costs and of the generator constraints that are given here. So I asked MATLAB to find the optimal or local optimum solution to my problem, and this is what MATLAB found. We have in red the nodal values. For example, here at node 1, I see that the voltage magnitude is 1 and the voltage angle is 0. Well, this is not surprising. This is the reference bus. I find that the injected power is given by this 400 active power, 80 reactive power. So that means generator 1 is running at the maximum of its capacity here. And generator 2, we have similarly voltage that is slower in magnitude. So there is a voltage drop from node 1 to node 2. And the voltage angle is also negative. So there is a reduction in the voltage angle from node 1 to node 2. We can also observe where power is flowing. There are two flows of powers in an AC grid. There's at least two. There is the active power and the reactive power. In reality, there is more. If we want a very detailed analysis, there is also power flowing at harmonic frequencies, but in good design grids, this is very small. In well-designed grids, this is very small, and we will ignore this in this lecture. Here we have 64 units, so that's megawatts, flowing from node 1 to node 2. The arrow here is not necessarily showing the direction of power flow, it's showing the direction that means a positive number. So if I have a positive here, it means it's flowing in the direction of the arrow. I need to take a convention, and I arbitrarily took this convention by starting from the reference bus. So active power is flowing from node 1 to node 2, and reactive power also is flowing from node 1 to node 2. We observe something here is that in the direction of active power flow, we have a reduction of the phase angle. And that is not just accidental. This is a pattern. We will see in a few more minutes approximation of the power flow that explains that very easily. But that's the first thing to remember. the active power flows in the direction of decreasing complex voltage angles here. Same here, we see that the reactive power flows from 1 to 2, and we see also that the voltage magnitude decreases. This is another pattern. We will not see it in detail, but that's a well-known pattern, that reactive power tends to flow in the way of reduced voltage here. We see also that generator 2 is not generating at its full capacity, and generator 3 is generating a small amount, and there is power flowing from generator 2 to generator 3, which is the large demand, and also from generator 1. We see here that the lines are limiting, and particularly this line, line 1, 3, has a limit. I guess this is line 2, 3 has a no, line 1, 3 has a limit of 300, and the other lines have a limit of 200 for this one and this one here. So the lines are limiting. Ideally, we would like to generate this one at full power because it's way cheaper, but we cannot because of the limitations of the lines. This is what this optimal power flow will capture here. The optimal power flow also gives, of course, the total cost, which is here the cost of operation here in per hour, because we're talking of power. And we'll also compute the losses. There are losses because the lines have a non-zero resistance. Therefore, there is some active power loss here, which costs something. So of course, the losses are expected to be small, which is the case here. We have 700 of total consumption and 700 plus the losses of total generation here. We also see red numbers called lambda here, which are the marginal costs. We'll talk more about them in a few more minutes. The marginal costs are the cost of an additional unit of demand. So the marginal cost of node 1 means if the load would increase by, let's say, 1 megawatts, then the additional cost would be 69 franc. So why 69? Well, that means that in order to generate here, we would need to probably do a mixture of sending less to node 3, which means generating more at node 3, which has a very high cost here. In contrast, we see that at node 2, which is not saturated, and the line is not saturated in this operation. So if we increase the demand here by a small unit, 1 megawatt here, this increase in demand can be fed entirely locally. So the marginal cost will be 1 franc per megawatt hour. So we see that the costs here at the 3 nodes, the marginal costs are very different. And this is an important number that is used in electricity markets here. We see that if you sit at node 3 in this grid here, the marginal cost is 226, whereas at node 1 it is 1. And we can understand this large difference by the symptom of the fact that this grid is very limited compared to the capacity. To see that more clearly, if I replace the line limits by a factor, I multiply them by a factor 10, what changes now? Well, we will see that if the grid is practically non-limiting, because I multiply everything such that the capacities of the lines are way above the total demand of this grid, then of course, what we expect is that we generate everything at node 2, which is the least expensive one. So it's running at full capacity. And we see that the direction of power is now changing. There is negative value here. That means node 2 is exporting to node 1 to go via node 3 here. We could ask ourselves, why is node 2 exporting to node 1 and not directly to node 3? Why does it need to flow somehow this way in order to get there? That appears to be inefficient. And it is true that if we had full control of the power flow, if the power flow would be like a road or a computer network traffic system, then we would send everything here because there's enough capacity on the line and there's no reason to send something here. The reason is that's the physics of electricity grid. You cannot say to a megawatt, go this way or that way. The only thing you can do is by generating this or this more, you change the complex voltage in the form primarily of the voltage angles here. We see that if we think of active power, the angle of generator 2 has now become negative. positive here, so that power can flow from generator 2 to the rest of the grid. And the angle of generator 3 has to be the smallest one because all power is flowing here to generator 3. Therefore, the angle of generator 1 has to be somewhere in the middle between 2 and 3. And by necessity, some power will flow from 2 to 1. The equations of active power and voltage angles are exactly similar to the equations you would have in a water network. Think of the angle as the altitude. Those are water reservoirs where you open the tap and you have water that can flow. Water will flow from the highest altitude to the lower altitude here. And this is exactly how power will flow. So if you want to control where power is flowing, you can open the taps more and less. That will change the voltages and indirectly change the voltages, change the power flows here. So we see that controlling the power flows in a grid, which is one of the objectives of the optimal power flow, which we'll be able to exercise in particular in the lab, cannot be done directly. We need to cast this as an optimal power flow problem and rely on the optimization. Unlike what we do in graph theory, where we could say, I want this to go this way or that way by playing on routing tables, here, this cannot be done. This is why the OPF problem is so important. It controls the cost of a grid, it controls who sells what in an electricity market, but it is also used to understand how power should flow in an electricity grid. I've shown here a very simple version of the optimal power flow, where there was only one timestamp. In the labs, like in reality, we'll see that most of the time we're interested in a multi-time step problem. For example, in what is called a dispatch plan. A dispatch plan is what we do when we want to do a plan for the generator. Typically what is dispatched is a generator. In the future, we will also be able to dispatch consumers because they may have batteries and electric cars that can be charged at a time that can be controlled. If we do that, then we control not just what we do now, but over multi-time steps. So here I'm assuming a 1 day ahead dispatch plan where I have one set point to control every hour. And then other than that, we simply repeat all the constraints one per time step. Plus, typically you have also what is called ramping constraints. A ramping constraint is saying the constraints on how fast generators can change. This is particularly true for technologies that are based on fuel-based generation. We will see also when we have batteries in the lab that this adds additional constraints which are related to whether there is enough space in the battery to store energy or whether there is enough stored energy in the battery. That will, of course, add constraints here to your OPF. Voilà, let's do a little break for a quiz. Here I'm showing, again, the result of the optimization problem for the toy grid I described a minute ago. I'm proposing two statements, A and B, and I'm asking you to say which of those two statements is true. Pluton, may I ask you to start to publish the poll? Thank you very much. So the first statement is about the power exiting node 1 into line 1,3, node 1 into line 1,3, versus the power exiting node 3 into line 3,1, which is the same line, but at the other end. And the other one is a statement about the sum of active branch powers exiting node 1, whether it is equal to this and whether those two things are equal. So, what's your opinion about those? Which of those, if any, is true? So you should see a poll on your display, and you should be able to click. Okay, let's close the poll in a few seconds. Pluton, can you close the poll and show the results? So the majority says B, which is the correct answer. Let's see why. Here, those numbers are giving the power that is injected here by node 1 into the line, which is given in algebraic form here. The power injected is, of course, has a negative sign is in the opposite direction at the other end. But if we look at it carefully, we will see, if I put a minus sign to count the power that's exiting line 1, 3 into node 3, I will find those numbers here. And there's a difference here. There's a small difference for the active power and a larger difference for the reactive power, which means here there is a power loss here. So the reactive power loss is not a big deal because there is no energy transported with this, but this is a real loss of power. So the sum of the two powers, if we have the exact values, are the losses here. And those active power losses are heat. They are dissipated in the form of heat into the line here. So of course, this should be kept as small as possible, but this is unavoidable. There are always some losses into a grid here. About reactive power, we may wonder, why do we have reactive power here? Why don't we put it to 0 everywhere? There are multiple answers to that. The first answer is that, well, we have seen that there are reactive power losses on the line. So even if we don't inject any reactive powers, then the lines will generate some negative reactive power because of their inductance, typically. So in an AC grid where the lines are not extremely small, the reactive power is always present because of the lines here. So we could say, well, why do we care? But since we must have power balance, if the reactive power is consumed somewhere in the lines, it must be generated somewhere. Otherwise, there will be problems. So that's the first part of the answer. Second part of the answer is the reactive power increases the module of the power and therefore increases the active power losses here. So ideally, if we have, so the current intensity takes into account it takes into account the reactive power. And as you know, if ideally the reactive power should be set to 0, that would reduce the resistive losses of the line here. So one of the second reason for reactive power generation here is to mitigate the losses in the line, make sure the losses are as small as possible, which is taken care of by our optimization objective, because we want to reduce the total cost. Obviously, the losses are incorporated in the cost. So we will, at least indirectly, reduce the losses by minimizing the cost. The third reason for the reactive power is also voltage control. We have seen that voltage magnitude is related to reactive power flow. So if there is a big voltage magnitude difference somewhere, one way to mitigate it is to use reactive power injections or consumptions to reduce its amount here. So reactive power management is always present in AC grids for all of these reasons. Voilà, we have seen a first complete view of what the OPF is about. And in the labs, you will be able to see how we can use the OPF for various purposes, like voltage control in a grid with a lot of solar panels, PVs. What we still need to do is, in practice, how to use it for real. What I mean by that is that once I have cast my OPF problem as a optimization problem, I have a lot of technical difficulties. One of them is that the problem is hard to solve. So apart from small examples, we're not able to solve it exactly, or even in small examples, we'll find only local minimum. For very large example, we need very, very sophisticated solvers. That's one way to go. But we will see also that there are convexifications, simple convexifications that make it more tractable, in particular, if you want to use it repeatedly to do control actions. And this means that we will need to manipulate optimization problems. So in the coming hour, what we will talk is about optimization problem, the kind of optimization problems we find in power grids, and how we practically need to manipulate them. So the first thing is to be aware of the difference between convex and non-convex optimization problems. In the world of optimization, there is really a boundary between convex and non-convex. Convex problems are the problems that we can efficiently solve today. Non-convex problems are the ones that we can solve only approximately. If they're very small, in some cases we can solve them exactly, but even then, very often we can solve them only approximately. And when they are very large, there are many issues. We can always solve them approximately, but we're also taking risks. The risks are that, for example, the optimizer does not converge. And this is things that have happened in the past, for example, in large grids where the solver was stuck in an exceptional case that happens very rarely. But since there is no theoretical guarantee that it will converge, this may be an issue here. There are two reasons for a problem to not be convex. One is the nature of the problem, that the equations are non-convex. The other one is that we have discrete variables. So discrete variables are, for example, whether we start a generator or not, and those kinds of things we will always find, as we will see here. So first, a small recap on what is a convex optimization problem. A convex optimization problem is a problem of this kind. It's an optimization problem that can be cast as a minimum. Of course, an optimization problem can always be equivalently expressed as a minimum or a maximum by changing the sign. If you replace F0 by minus F0, you go from one to the other. But if you want convex problems, you need to combine things well. So one way to formulate it is to say that the optimization function is convex. Here's a prototype of a convex function. The well-known convex function is x squared, for example, here. And the set of constraints may also be convex. A set of constraints is convex if any chord that goes from 2 points stays in the set. So left is convex, right is not convex here. So if we minimize a convex function over a convex set, then everything is fine and easy. In particular, any local minimum is an absolute minimum, and gradient descent, if we go down following the slope, we will certainly, with certainty, we will go to the global minimum. If we want to maximize, then of course we need to maximize the opposite of a convex function, which is called a concave function. For example, square root is a concave function. And same thing, if we maximize a concave function, there is a unique maximum that would be at this point here if the set is convex here. For real numbers, the set of real numbers that are convex are simply the intervals here. And of course, if we have a non-convex and non-concave functions, then we see here that there are two local minima. And if you do gradient descent starting from here, you may get stuck here and never reach that global minimum that is here. This is the problem and the symptom of non-convexity. How do we know if a problem is convex? Well, there is a number of tricks here. We will use primarily very simple examples, but it's important to be able to know exactly. So a function is convex, that's the definition here. But in practice, we see also if the function is differentiable, it means it's convex if the tangents are above the function, which is given by this expression here, or also that the matrix of all second derivatives of the function, if it exists, is positive semi-definite. Then if we combine convex functions by taking a sum weighted by positive numbers, we remain convex here. And something that we will often use, the maximum of convex function is also convex. The combination also is, but we need to be careful here. We need the thing that we combine to be increasing here to respect all the order here. So those are some of the catalog of functions. The primary one we will use is the number 5, where we will very often use max in the context of optimization problem. Why are convex problems special? Well, this is illustrated here. If you have over here, I'm showing a function of one variable, which perhaps makes the problem too simple. Over a convex set, that means over an interval, this function has a local as any local minimum is a global minimum. Therefore, it will be very easy to go there. If you start from any point, you follow the slope, and if you follow the gradient, you will automatically go to the minimum. In contrast, as I already discussed, if the function is not convex, many weird things can happen here, which is also a symptom. If you find a problem that has multiple local minima, you know it is not a convex problem here. So let's test our understanding. Here are 3 problems. Which of them are convex problems? Okay, can we, okay, poll closed. No, poll not closed. I see now the results. Thank you, Pluton. So you've seen the results. The majority says G, all, which is not correct. Let's see which one are or are not convex problems. So the first one here is not a convex problem because we're maximizing x squared. In fact, if we maximize x squared, where is the maximum? Where it is either at A or at B, or perhaps at both. If A and B are opposite, the maximum here will be reached at both ends. So in fact, if we maximize a convex function, x squared is convex, but we're maximizing. To maximize a convex function over a convex set, then the maximum is at the edge of the domain here. And in particular, there might be multiple maxima, which is the symptom of not being a convex problem. Sorry, there can be local maxima here, for example, at the edge here. Here, this is the prototype of the convex problem, because this is a convex function and the set is convex. So B is convex. And C, well, we have a linear function, which is the prototype also of a convex function. In fact, very often when we speak of convexification, it means linear functions or easy combinations of linear functions. So this is certainly linear is convex and is concave, by the way. So maximizing this, because it's a concave function, fits the first thing. Now, is this a convex set? Well, we have linear inequalities, and linear inequalities also always provide a convex set. So C is, C is a convex problem, and D is a convex problem. So the correct answer is F. In the interest of time, I will skip the next poll and continue here about a special case of convex problems that you all, of course, encountered, which is linear programs. So linear program is a special case of convex problem where the objective function is linear. Now it can be min or max because it's both concave and convex. And the set of constraints are given by linear inequalities and or equalities here. So of course, this is a convex problem. And this is very often used because there are very, very efficient algorithms to solve problems of even very large size here. So of course, if we have max or min, that gives exactly a linear program. So there are multiple ways you can define a linear program. Here's what happens for a linear program. Here, the problem C that we saw a minute ago. In gray, I'm showing the feasible area. We say that X and Y should be non-negative. And I have two linear constraints that correspond to those two lines here. So this feasible set is this one here. And now if we want to find the max of this, then the max will be reached at a local maximum. But because it's both a convex problem, but also this is maximization of a convex and concave function, the max is also obtained at the edge. So what is special about linear problems, you never find an optimal point that's in the middle of the convex set of constraints. It will always be at one extremal point. In this case, that's the point here. So if we ask MATLAB to solve that, it will give us the answer, this point here. Graphically, we could do it here also. We're trying to maximize x plus y. So if we plot a line parallel to the second diagonal, we'll try to move the further up, then we stop at this point here. So that's the maximal solution, the optimal solution here. Whether a problem is can be formulated as a linear program or not is an important topic. We will see, in fact, that we are able to transform many problems that are not linear programs into linear programs. So one of the skills we must master in this module is this problem transformation. So here I'm showing two problems, A and B, that are defined on the same set of linear constraints here. The objective function of A is a square, the quadratic function, the norm of x squared plus y squared. The second one is a function that is given as the maximum of two linear functions here. Which of those problems can be formulated as a linear program? I close the poll in a few seconds. And the majority says B, which is the correct answer. Let's see why. Well, A is a convex optimization problem. Now would be a bit too long to explain exactly why it cannot be made linear, but if it would be possible, first hint is we would know how, but in general, unfortunately, it's not possible to transform exactly a square into linear things here. But it's possible to do it approximately. And to make it approximately, we can use the same transformation as we're doing for problem B. Oops. And the trick is the one I'm showing here. So problem B has linear inequalities and therefore a constraint set that is convex. But the objective function is this weird thing, the maximum of two linear functions. So if we plot the maximum of two linear functions, if we draw, we will obtain something. Oops. If I plot the maximum of two linear functions. Here is the first, here is the second, and the maximum will be this function here. Right. So the max is convex here. We have seen also that's one of the properties of convex functions, but it's very clear here. If we draw, it looks more like an x squared than, the prototype of the convex function is x squared. The prototype of the concave function is square root. So this is more like x squared. So this is probably convex, and we can check that here. Now the trick is to say that the max of linear functions can be replaced by this transformation here. So if I look at the problem, I replace f0 by an additional variable. So I add a new variable to my set of optimization variables. I have t, and I add the constraint that t must be larger than both of the components of the max here. Intuitively, because the only constraint on t is that it should be larger than those two, and if I want to minimize t, I will take the smallest value that is larger than the two. And the smallest number that's larger than a and b is the max of a and b. So if I want to optimize this, I will be forced to take t equal to the max of x plus y and 2y, which is exactly this thing here. That's an intuitive explanation. If you want a more rigorous one, here it is. In general, if I look at the set of xy that are feasible for problem B, right? That's the constraint here. So I call x here as a shorthand notation to reduce to avoid writing too many equations. My problem B can be written as minimizing t subject to the constraint that t is larger than f0 of xy, which I'm plotting here. On the x-axis, I put xy. On the y-axis, I put t only. And in problem B prime, I have enlarged the constraint set to this pink area, which is all the values of t that are larger than or equal to the f0, which is the objective of my previous problem. Now the question is, if I want to minimize t over this pink area, where should I go? Well, I should go to the point of the boundary, which is as low as possible. And the point of the boundary, which is as low as possible, the boundary is f0 of x, of the x-axis. So we should go to the value that is as low as possible here. This is a more formal explanation of why this transformation works. We will use that transformation very often. Therefore, I give it here a theorem that is a quite generic one. If we have an optimization problem where the objective can be decomposed as a sum of terms, where many of the terms, in fact, all but one, are expressed as a max of things. So f1 is the max of some g's here. Then for every term in the objective function that is a max, I can replace it by an additional variable here. I replace f1 by t1, I replace fn by tn. So I will add here n optimization variables here. And the objective functions will be now t1 plus etc. plus tn plus h here. And I will replace, I will of course need to add a constraint where the constraint that t1 is larger than each of the components I had in the maximum here. So this is exactly what we did in the previous case, where we had f0 being the max of x plus y and 2y. I added one optimization variable and the constraint that this optimization variable must be larger than all of the components. And for all the arguments I gave before, then it's fairly obvious that the two are equivalent. So this seems like a completely obvious thing, but what is the value of doing that? Well, the nature of the problem that I have here is different from here. In particular, whenever f1 is a max of linear terms, all I have here is I have added things that remain linear, and the constraints, if all the g's are linear, will be also linear. So I will transform something that is nonlinear into something that is linear here. So that's very, very often used in all energy constraint systems, where we replace complex things by max of linears, and then we, at the end, have linear problems.